Never in your life have you held a flask with all positive charges. At least I hope not. Never in your life have you held one with all negatives. We have to have things balanced in solution. We know that. That's our classic example we bring up in class all the time. So the total amount of positive charge that I've got has to equal the total amount of negative charge I've got. That's the idea of a charge balance. Now let me go ahead and come up with an example case just so we can kind of think through how this equation should look. Suppose that in solution I've got NaCl. Well, right away, if that's all I have, the concentration I have of NaCl, well, we know that the amount of sodium ion we have has to equal the amount of chloride ion. Not only because we made them from the same species, but because if that's all that's present, these charges have to match each other. Now let's make things a little more complicated. Let's say that we've also got H plus coming from sulfuric acid, and we're going to have the sulfate ion over here. Alright, we can see though we're going to need to have a little something extra to handle things, because look, every time that I add one sulfate ion, I end up with 2 minus charges. And if I'm trying to say that I've got the same number of positives as I have negatives, we've got a bit of a complication. And so the form for the charge balance equation actually needs to account for that somewhere. So what we're going to do is we're going to put the charge in front of each of these, at least the magnitude of the charge is going to go in front of those as a multiplier. Because in other words, if I have 2 sulfate ions, and this is my concentration, if I multiply that concentration times 2, I now know how many negative charges are present. Here I'll be multiplying by 1 there as well, and by 1 there too. And so that's what it's going to look like if I were to set up an equation to say that I've got the same number of negative charges as I do positive charges. You might be saying, well, wait a minute, no, that doesn't look right. How can this all work? Remember, we don't know what numbers are being plugged in here yet. And if you need to be reassured, keep in mind we're going to have twice as many H pluses for every one of these molecules that we had. And so, it should all work out. That means we can go ahead and turn this into a much more generalized form. So the general form of that is going to be, I'm going to use C for cations, and I'm going to use A for anions. We're going to have one of these cations and its charge plus another cation plus etc. equals, we can set things up the same way over here. The charge goes in front, anion number 1 and we should probably actually have an extra subscript there to specify that it's anion. So 1A, we'll call these 2C, 1C. Not exactly how you'll see it in the book. In fact, they used M instead. Whatever. We're just making up our own notation so we can see what the equation will look like. Then we'll have our N2 for anions for anion number 2. This is the general form that we'll have for a charge balance equation. Now, the key part of this I also want to point out. We just got done talking about activity coefficients. Activity coefficients are all about how things are sticking to each other. But this equation isn't. The charge balance is all about what's the absolute count of ions on both sides. So activity coefficients should not appear here at all. We're not simplifying things. They shouldn't be here. So I'm not being nice. I'm just making sure we're being rigorous. So that's the basic idea of our charge balance. Now notice that if we have a complicated problem and we have to start doing some substitutions in order to solve it, we just generated a new piece of information based on things that we already knew. And the more pieces of information we have, the more that we can rearrange and substitute and finally solve things. That's going to be a cornerstone of the systematic treatment of equilibrium.